All right, kiddos, let's try a couple of examples using our new photoelectric effect equation and some of our conceptual understandings. All right, so a photosurface has a work function of 1.5 electron volts. Find the critical frequency. Just as a reminder, 1 electron volt is 1.6 times 10 to the minus 19 joules. All right, so if the work function is 1.5 electron volts, that means the work function is 1.5 times 1.6 times 10 to the minus 19, right? And if this is electron volts, really, what this conversion factor is how many joules there are for every electron volt. Okay, and we can get that as our work function. Okay, in my example, in my notes, I just do it all in one fell swoop. And so we can say that the kinetic energy of our emitted electron is HF minus the work function, but we know at the critical frequency, the kinetic energy is 0. So we get HFC equals the work function. All right, so Planck's constant is 6.6 times 10 to the minus 34. We're looking for that critical frequency, and that equals our work function, which is, again, 1.5 electron volts times 1.6 times 10 to the minus 19 joules per electron volt. Okay, and when we do that calculation, we get the critical frequency is 3.6 times 10 to the 14 hertz. Okay, and if we looked at published critical frequencies for different materials, we could identify the material based on that critical frequency. All right, and then if the light of frequency 6.1 times 10 to the 14 hertz falls on the surface, what is the energy and speed of the emitted electrons? Okay, so the first thing that we want to do is actually check, because sometimes these are trick questions, and the frequency that they're giving us sometimes is lower than the critical frequency. So if the frequency of light is lower than the critical frequency, the energy of the emitted electrons is 0, and your answer is there were no electrons emitted because the light didn't have a high enough frequency for this material. We, however, have a high enough frequency that's above the critical frequency, and so we can proceed as normal, just using EK equals HF minus our work function, and that should be a standard plug and chug. EK equals 6.6 times 10 to the minus 34 times 6.1 times 10 to the 14 minus our work function 1.5 times 1.6 times 10 to the minus 19. Okay. All right, so we can get our kinetic energy here, which is 1.64 times 10 to the minus 19 joules. Okay, that's the kinetic energy. But this question is asking, what is the energy? Okay, cool, we got that. And what is the speed of the emitted electrons? Okay, so now we can take this. We know it's a kinetic energy, so we can set it equal to 1/2 mv squared. Okay, where if you remember the mass of an electron is, what is it? 9.1, I think, times 10 to the minus 31 kilograms. Is that right? Didn't write it down when I did my notes here. So I think that's right. But if you use the right mass of the electron, you get a speed that's equal to 6.0 times 10 to the 5 meters per second. So those little guys are booking it there, going super duper fast. A little tiny amount of energy means little tiny things are going really super duper fast. All right, so let's take a look at one more example. This one includes some tricks, so you're going to want to pay attention to these. So monochromatic light, that just means one color, one frequency of intensity 4 watts. Hey, we don't have any equations for wattage and the photoelectric effect. Don't worry, it will be okay. Intensity of 4 watts and a wavelength of 4 times 10 to the minus 7 are falling on a photo surface whose critical frequency is 6 times 10 to the 14 hertz. It releases 10 to the 10 electrons per second. What is the current collected on the anode? And the anode in that simulation, if I pop it up here, this would be the cathode right here. What's releasing the electrons? The anode is just the other side, right? You saw that when the electrons reach the anode, that's when current was able to flow. All right, so what is the current collected on the anode? Okay, so there's a lot of information here that is mostly not relevant. We're looking for current. Right, we don't have like in our photoelectric effect equation, there is no equation for current. So might as well just start out with the definition of current back from about this time last year. Current is the charge flow rate, right? Coulombs per second. So how can we use some unit analysis to get coulombs per second? Well, we know that 10 to the 10 electrons are emitted every second. Okay. And so we've got seconds in the numerator, but we've got electrons in the, or seconds in the denominator. We've got electrons in the numerator. So what can we do with that? We want coulombs in the numerator. Well, we do know that an electron has a charge of 1.6 times 10 to the minus 19 coulombs for every electron, right? So these electrons can cancel, and we end up with coulombs per second, and this is all conceptual. And so we end up with a current that's equal to 1.6 times 10 to the minus 9 coulombs per second, amps. Boom. Okay. Now, the next thing is if the intensity of light is increased to 8 watts, what will the current be? What? We still don't have a relationship, right, that relates wattage to current, like explicitly. But what we do know conceptually from the simulation is that the wattage increased the current proportionally, right? So if we double the intensity, right, the current will double. Okay, so we're just going to take the current 1.6 times 10 to the minus 9 and double the intensity, which is represented by wattage or power, we double the current. So 1.6 is doubled to 3.2 times 10 to the minus 9 amps, right? It seems tricky, but again, conceptual answer is necessary here. All right. Now, if the light intensity is 8 watts, right, that's the hint that we're going to be using this current, if that's necessary, and the wavelength is 6 times 10 to the minus 7 meters, what is the current? Okay, now this one is going to be a little bit tricky because you might say, oh, it seems like this is 8 watts, so we will use this current, but they're giving us this wavelength. We know that current increases proportionally with intensity of light, but we also know that the wavelength or the frequency tells us whether current is emitted in the first place. So let's take this wavelength and turn it into a frequency. So remember, speed equals wavelength times frequency. Frequency equals speed over wavelength. We're looking at the speed of light here. And so we've got 3 times 10 to the 8 meters per second, and the wavelength is 6 times 10 to the minus 7 meters. And so the frequency is 5 times 10 to the 14 hertz. Okay, so who cares? Well, let's scroll back up here. 5 times 10 to the 14 hertz. Here, in the original description of our problem, it says the critical frequency is 6 times 10 to the 14 hertz. So what are we seeing here? We're seeing that even though the power, the intensity of light is 8 watts, doesn't really matter because this frequency is less than the critical frequency, right? The critical frequency was 6 times 10 to the 14 hertz. And what does it mean if the frequency of light is less than the critical frequency? It means there is no current. Okay, because we aren't up to the frequency of light that has enough energy to emit an electron. Okay? All right, so the last thing that I'm going to have you do, I'm about ready to run out of time on this video, but please take a look in the textbook about technologies that use the photoelectric effect. Again, this is what Einstein won his Nobel Prize in Physics for, is for the photoelectric effect. We use the photoelectric effect to take digital images. CCDs and CMOS sensors use the photoelectric effect to create digital images. And then also photovoltaic or solar panel cells use a PN junction style silicon to gather light, emit electrons, and create a complete current that allow electron to flow through your home. Okay. All right. Take a look at these places in the textbook and give the problems a try on the Google Classroom. Let me know if you have any questions, you guys. Good luck.